Okay, so let's start. Good morning, everyone. We're here to give you some highlights and tips about the coding challenge. We have Filippo Spiga and DK Panda and his team from X-ScaleSolutions. So I would like to start with Filippo. Filippo, maybe start by showing your slides, and
absolutely.
After that we'll continue with the DK Panda.
Sure. Let me share. Okay, can you see my slide?
Yeah.
Okay.
Good.
So thanks everyone for tuning in. You already had a few sessions about the other task of the student cluster competition, including highlights of the various application and challenging, etc. So I will spend the next, let's say, 10-15 minutes. Obviously, there will be plenty of space for Q&A as well during this hour slot to talk about the coding challenge that we're gonna have this year. Information already made public on the wiki, so I'm gonna repeat some of the things that are already essentially written there. I will give maybe one example, few additional tips, but I'm not going to disclose too much because this is supposed to be a coding challenge. So there's obviously something that you have to do by you guys as a team, and I don't want to tease out too much because it's also competition. And so each one of you has to come out with their own solution and their own ideas. So for the coding challenge, we decide to use one application that you already are going to use for the normal classic benchmarking, tuning, scaling, etc. that is Compat ready. Sylvain, our collaborator, already spoke to you, I believe this Tuesday, about the app. What is the science? What is the implementation? He probably give you an highlights about what are the bottlenecks, more or less what's the structure, so on and so forth. It's not a secret because I saw his slides and he's mentioned very clearly that this application perform a lot of MPI all tools. So, collective communication that involve all the MPI processes, all exchanging data at the same time. And based on scaling factor, based on type of input, based on the type of machine, the type of interconnect, the application can become communication bound and so dominated by essentially MPI all tool. And these MPI all tool are happening across the application all over the place in various locations. If you look at the source code, and probably you already start to look at the source code, you will notice that the part of the code that implement the fast Fourier transform in the 3D domain and the transposition, these two steps, it's this 2D decomp type of library that is embedded in the source code. So the coding challenge will look at the application and the use of this library inside with some specific constraint in terms of input and in terms of machine viability. Yes, so we have 5 tasks for this coding challenge. The first one has no points. Is essentially you getting familiar with the system, and we want you to get familiar with the system, running synthetic benchmark, understanding a little bit about how to offload certain collective communication, and DK and his team will talk about it on the DPU. But then obviously the focus is about modifying the application and try to leverage essentially this interesting piece of hardware. I will go through the detail, but obviously there is a starting point. We want you to benchmark and understanding what this starting point looks like. We want you to do some code modification. We'll go through what's allowed and what's not allowed. And then obviously benchmark and evaluate and profile after the code modification. And when you're happy with what you get through few iterations, write up some sort of summaries of your finding and results. And then out of a couple of constraints that we set to make the coding challenge achievable, if times allow, if you are interested, you can always get an extra, which obviously will be if you do this extra, we're gonna get extra point. But do this extra where you also allow to change a little bit the input and understand a little bit better the behavior when in a more uncontrolled, let's say, scenario. So I'm going to focus on explain a little bit more. Well, I would essentially read it and go through a little bit more, eventually in detail. The key 3 points. So task 1, task 2, task 3. Task 4 is basically repeat the same, but with less constraints. So there's not much to say about it. I think it's written very well. So the first task, obviously, once you get familiar with the DPO, get familiar with the environment, you're understanding how the library works, you experiment with synthetics. The first task will be take the code, modify to change from a blocking to non-blocking strategy. I will give you a, between brackets, fake example. I'm not going to show you the real code from the application. This is a coding challenge. So just a fake example to explain the idea. And then obviously run the application before and after and see what happened. So this is very important in terms of constraint, in terms of what's allowed or what's not allowed. So we want you to focus on a fixed version of the application, that is version 4 that you can get from the public GitHub. Why a fixed version of the application? Because I want you to submit the entire code you modify, and I will do a literally diff of the reference version and your version, and I will look at what you did. So if you start to diverge from the reference version, the submission is not valid, essentially. So you need to be able to be a diff between the new one and the reference one. The application is a little bit of a work in progress type of project. So they're still developing and adding new science and new models and new feature, changing a few things in the main app. So start with the reference one. So we're all on the same starting point, same page. And what you can do is essentially change whatever you like. So we're not really, putting any particular constraint here. There are obviously a couple of suggestions just to not to consume too much time where it's a dead end that I'm going to give you along the way. But obviously you can change anything you want to change. For as long as the results compared to the reference version is correct, it is reproducible. I will go through this again probably in a later slide. Reproducible means that when you submit your script to me, and obviously the input is going to be fixed, cannot be changed. I take your code, I compile it, and I can run and get, with plus minus some variability, because no system is perfect, I get the results you actually claim in your final report. I will stress on this, but I will mention again toward the end. The reference machine we are using is Tor, the cluster, the X86 cluster with the DPU card hosted by the HPC Advisory Council. You can do your development somewhere else. You can do your tests somewhere else, but that's the machine where the code has to compile, has to run, and I have to be able to reproduce the data. So if you come and submit something and say, oh, but it was working somewhere else, the submission is not valid. It needs to work on Tor. What is not allowed in terms of code changes? So obviously, and like any real application, there is some I/O involved. You can't touch the I/O. So if it does the I/O, it is what it is. We don't want to change the input file, a part of few parameters that are described for the last task, but we give you a fixed input case, which obviously has baked a specific type of physics we want out of this problem. Changing the physics may affect the number of FFT you do, the number of transpose you do, the number of MPI all tool that you do. And we don't want to do that. We have things to be reproducible. And also changing the version of the code is not allowed. This version has been tested with the input we're going to provide. So there's not supposed to be any bug. Finger crossed, never say never. Maybe you discover something. But so far has not been anything, everything works so far. So the code is fixed, the version is fixed, cannot be changed, unless for some reason we communicate to everyone that it's possible because we found a very serious bug. But I doubt this will be the scenario. So this is the first task, and it's the bulk of the work. So obviously the challenge is composed, I would say, by 3 major points. You need to modify the code, profiling and understanding what's going on, and then also report about what you did. So explain that part. So the next big task is obviously performance assessment of the original versions versus the modified version of the application. So you take the first one, you take the cylinder input case, you have a specific problem size. With that specific problem size, with that specific input, you can play with some parameter in terms of job size, number of processes per node, and things like that. So we give you up to a maximum of 8 nodes. I think it's maximum 8 nodes in a single job reservation. So feel free to experiment within this constraint and use the resources that are available within the node. And the objective of the profiling activity will be to understand if MPI overlap, I will explain what overlap means, is happening. you can measure it in some way, okay, understanding what's going on, and obviously being able to document it in a later stage. So in terms of submission, obviously we need the code. This is kind of obvious. We need to know how you run it. This is kind of obvious. We would like to know, we would like to see your baseline data before and after the application is modified, and a little bit understanding what's going on. You will see from the synthetics, and you will see from the application itself that not all the time offload is convenient, and sometimes the offload is more effective in a specific range of exercise, in a specific number of MPIs. Probably DK and the scale is going to go through this information, but try to understand what's going on. Profiling is obviously the tool that allows you to do that, and you can pick up whatever profiler you want. I mean, we mentioned two, but if you're familiar with another tool, fine with it, for as long as it's you can get some measurement. And again, both when it's so both with this with and without the offloading, okay, so with and without the changes, the code has to be correct, obviously, and has to give the same results. That's kind of obvious, the same result for any given input and set of execution parameter. So means in that you vary the number of MPI processes, the number of MPI processes per node, the results should not change, and things like that. So you did the code changes, you understand what's going on, you have some data pre and post, you put together a report. The report can be in form of slides, can be in form of document. I don't mind. We're going to read the report and we try to understand from the report if you understand also what's going on in terms of MPI behavior, if you did some profiling and how deep you went through your analysis. And also from the report, we would like to understand a little bit more how you divided the work within the group, within the team, and who did what, and if there is any specialization in terms of your task or your knowledge. Try to describe that part as well. So say more the human component, not just the code component. The report, it's important. The code also speaks by itself. So I mentioned in a previous slide, submit your code modified, but if you add the comments, if the code is clean, so for me, it's not a nightmare to go through the diff process, understanding what you did, it's appreciated. So, the code itself is a form of report if it's done properly and it's written well. And obviously in this step, because this is a competition, we also gonna rank you. So essentially, so we're gonna take the best result you get after adding the offloading, and put together a ranking of everyone who submitted a working code, and use these as well in the judgment criteria. It's not only that, but it's also obviously it's a competition. It's also part of the competition. It's just it's part of the challenge. So what the code looks like, so you can start to dive into it and understanding a little bit better. As I mentioned, so you can see on the left, this is more or less how it looks like the Git, the repository, the source code. The main files that we expect you to change are in the source directory, which is all the solver, the various Fortran files. This is a Fortran code, as I didn't mention, all the files, etc., etc. The library that does this transposition FFTs is baked into the source code, is under the directory to the comp, decomp2d, sorry. There are a bunch of files. There are more files than the one that listed. Some file does the FFT, some file does the transposition, some file does the initialization. You will find the mail file to the comp underscore to the .f90 what are the interfaces of a series of prototypes that implement what are the transposition, which, as we show, is basically means the MPI all-to-all. And obviously, this code handles both complex and real. So this is a Fortran tricks. So based on the type of array you pass to the interface, it's going to call a complex function or a real function. But there are different transposition, because we go, as if you remember what Sylvain explained, from pencil in one direction to pencil in another direction, and then pencil in another direction. So you basically do multiple transposition one after the other, and that's it. So these are essentially the starting point, but obviously here are implemented in a blocking fashion. So this is more or less how it looks like, the transposition. How more or less there is more code in the real repository. I just reduce it for the sake of a slide. So Every routine does 3 major steps. Before calling the real communication, he has to rearrange the data in a specific way. This is dependent of, both the problem, both of what point the domain, the current domain is decomposed and oriented. So it does some memory rearrangement. He called all to all, and then or a version of all to all. You will see in the code that there's all to all and all to all v. This is, as I say, left as an exercise to look and read, but there is a communication essentially, and then it rearrange again the data in a way that can be consumed in the main application. So each transposition that you can see from a single API call inside is done by a memory rearrangement, a proper communication, and another memory rearrangement, which is important to do in this order. And this is repeated for each one of the combination: X to Y, Y to Z, Y to X, X to Y. And you will see when you look at the transpose, for example, transpose underscore X to underscore 2 underscore Y dot inc, there are multiple prototypes and they are more or less similar. What changes the indexes and things like that. You're free to change those one if you want, but as you will see, what we suggest is actually look at the operate at the application level. So this is the blocking prototypes. So what also it's within the 2D decomp, they're already baked, half coded, I will say, but you can find this information already out there, but half coded, there are non-blocking prototype. So the transpose X to Y is essentially splitted in 2 separated routine call. One is called transpose X to Y start, where basically what it does is post a MPI communication and immediately return control to the process. And another prototype that essentially is transpose X to Y wait, which is a blocking behavior, means that once the code arrives to this point, it stops and you waited that communication or the buffer is filled, so the communication is completed before progress with the computation. So one single call is split in 2 different calls, one non-blocking and one blocking, one to use to initialize the communication, the other one's used to wait that the data you need has actually arrived. And there are a couple of things that you can look at. So you can look at the code as it's in Xcompact 3D. You can take inspiration through the library that is also posted as a separated repository. But you will see that there is also extra code path inside the code. I would suggest to focus on the one that is marked as even, because it will be compatible with the input case that we're giving to you, which transform all to all V into all to all. And ignore for now the SHM path because it's way more code and may not lead anywhere. So just leave it for exercise if you have more time. So these are the 2 non-blocking prototype that then we expect you to use inside the application to essentially rearrange the computation in the application in the key part that are more communication demanding in order to implement a non-blocking strategy. So how are you going to do that? So this is an example, just to give you an idea. It's a fake code, so you don't see this code in the real app, but just to give you an idea. So the code here, you have 2 variables, 2 3D array, UX, UI. You do something with them, then you transpose them. The transposition, as you can see, are not done in place, are done out of place. So one array goes into the other. So UX1 contains a distributed piece of the array UX across multiple MPI. When you want to do the transposition, UX2 will have the same data but rearrange it accordingly by swapping pencil from X direction to Y direction. And so you need the data to be transposed for some reason. So you transpose UX1 into UX2, you transpose UY1 into UY2, and then you do something else, okay? And as you can see, the one in the last 2 statement, you need both of them, the transpose one and the non-transpose one. So this example, you just compute the first, compute the second. The first transpose is blocking, so it will the computation will progress only when the data is all being rearranged. There is another blocking, MPI in this case will be an all-to-all, and then it compute. So the first thing that you can see here is that in principle, the one in red and the one in blue are independent. So once you've done the first one, you can actually immediately call a transpose. The problem is that you have to compute in between something. And when you did the second one, you can post the second transpose. But the first transpose and the second transpose operate on complete different arrays. So in principle, they can be posted or they can be initiated at a different stage. So by looking at this dependency in the statement, which is purely derived by essentially reading the code, what you can do is to implement this with a non-blocking idea. And what's the idea here is that, okay, you start with compute UX1, then you start to communicate UX1. While you communicate UX1, you can do something else on UI. So and then you obviously, after that statement, you can start to communicate UI. At that point, you have two communication in flight. In order to compute X, you will have to wait. The UX1 is essentially being transposed into UX2. And vice versa. And the same story for compute Z. You will need to wait the data from X to Y transposition to essentially happening. So XY1 became XY2. So with this behavior, essentially what you observe is that these three statements can achieve overlapping of communication and computation, because you transpose X to Y start, return control immediately through your process. That means that while the MPI and the DPU are communicating, you can actually compute UI. And in principle, you can start to prepare and also start to communicate the second MPI all-to-all, while the first one is on the flight. You do need a sync point, though, in order to compute X. And at that point, this sync point, the code will essentially block and say, okay, now to progress, need to wait X2 to be all on the CPU, all on the process in order to compute. But there is some overlapping there, which, in certain condition, a certain scale, with a specific input, can lead to a performance improvement. And obviously, if this is repeated tens of thousands of times, this improvement is also reflected in the time to solution of the application. There's another overlap of computation and communication and another sync point that it's over there. So when you start to do the profiling of the code, you start to look at some of the more intensive routine, and you start to actually read the code and understanding what's going on, you will see that the code calls tons of this transpose, and it does a lot of operation on arrays. And in a lot of cases, you can rearrange the code, that's very important, without changing the final results, in order to actually achieve this idea of overlapping of communication and computation. Because this is going to be paired up with the right MPI library, the MVAP2 DPU, and the right piece of hardware, this is a DPU, your computation and communication will be truly overlap and leave the CPU being able to do calculation while communication is actually happening. Yes. So a final recap. Yes. So sorry, this is an example of submission script to submit. It's described also on the wiki. I'm pretty sure with the next talk, they go more into the detail about what's going on. In the way Tor is configured, you see nodes that are the DPU and nodes that are the real host, because every node, Tor 001, has the BF equivalent, so the blue field, the DPU equivalent. And this trickery basically makes sure that when you load MVAP DPU, you pass to MVAP DPU both the list of the node CPU and the list of the DPU you need to use. And then the MPI library will do its magic. From a code perspective or a compact 3D perspective, you build it with MPI like you build it normally, and you execute it like you execute it normally. The magic will happen because of the right MPI library and because you essentially enable the use of the DPU, and they will explain which flag to use. So it's not a complicated submission script. It's not something that requires tweaks except the number of nodes you want to run. But we give this as a template, and then you can bake every timing or monitoring or whatever you want to do into it. But this is essentially a working skeleton. So a final recap of the rule and what we expect, what we don't want to see, and things like that. Then I can stay. We can leave like 5 minutes for question or wait at the end for question. It's up to Ophir how he wants to manage. So what you can do again is to modify, adapt any portion of the code, and for as long as it's correct and result are reproducible. You can also do the development elsewhere. If you have for certain things you don't really need the DPU. It is needed when you start to do the profiling and the evaluation. But to understand if it's correct, you can try a non-blocking approach, even with in a local machine without the DPU. with the DPU, you will see the performance benefits, obviously. Now, what you cannot do is to change the version of the code. I want to repeat this multiple times. Change the input unless during the final task where we give you the ability to play a little bit with it. We don't want you to take shortcuts, meaning that's the reason why I want everyone to submit the entire source code. We provide you an input that might not trigger every single piece of the code, or you might find, I haven't found one, but you might find a scenario where by removing some statement, the result is still correct. Now, this kind of shortcut will not be tolerated, I would say. So I will look at the source code in depth to figure out if the only thing you did makes actually sense. So no shortcuts. And what you cannot do is essentially submit results or profiling output done on a different machine. Obviously, if you've done analysis on a different machine and you use those to infer some information, that's fine. But ultimately, what we want to see is that you've been using Tor to do, the key aspect of evaluating the DPU. So what we would like to see, this is, plus, I would say, something I would personally appreciate is a clear working code, clean and working code, meaning not too much messy, not too much code commented. Try to keep it clean, try to keep it readable, so I don't drive myself crazy. And a report, whatever slide or text, no preference, that somehow cover not just the results, but also the key point of your journey, how you get to understand that modification lead to an output that is valuable. So I'm interested to understand not just the how, but also the why you did certain things. So what's not going to be evaluated? This is a little bit tricky, but we're going to do our best. The focus of this task is to evaluating the DPU, so evaluating the improvement in the communication. Now, every code has room for improvement. So in principle, you can, you probably rearrange some computation step and you make it 3 times faster. That's great. But we want to focus on the communication step. So this is the kind of evidence that I want to look at the report, and if you understand, and the code modification beyond just the ranking, because there is rooms to modify the code and improve it from even from an algorithmic perspective. So we don't want to get to put too much constraint. But if we obviously see a time to solution improvement that is not linked or justified by the fact that we're using the DPU, we're going to challenge you to explain what you did and to figure out what is the DPU component and what is the DPU, let's say, contribution into the new time to solution. So essentially, the task is communication and DPU. That's the key. Everything else is a plus, but it's not going to be judged as part of the coding challenge. So if there are any questions, I'm happy to take them now or later. Ophir, it's up to you.
So what I suggest is if you have questions, let's take it in the end. But meanwhile, you can just type it on the chat if you want to ask. Let's do the second session with.
I will stop sharing.
Yeah. Professor Panda, and after that we'll take questions. Okay, so if you want to type them or if you want to say it at the end, it's okay.
Can you see my screen? I'm sharing.
Yes. Yes. We see the windows. We don't see
the. Okay. So just
maybe the other screen.
Yeah. I think just trying to share it. Give me. Just give me 1 minute. I think I have it open. Just. It's opening up.
Share again, maybe. You click on the arrow next to the. Yeah.
It's coming, I think.
It's coming. Yeah. Yeah. Now it's it. Good. Okay. Go ahead.
So is it in the presentation mode? It's okay?
Yes.
Okay.
Yes,
okay. I am always having this Microsoft Teams. I'm still getting used to it. Okay. So thanks, Filippo, for giving an overview. I am DK Panda. Some of my colleagues here, Nick, Danglai, and Hari are here. So I'll be going it a little bit overview about the MAPIS to DPU library, which all of you will be using. And you must have received already the licenses and a copy to the user guide. But I'll just try to provide a very high level perspective and what kind of things are there inside the library and what kind of things you can do to get better performance. So as you know, the MPI libraries you basically use like for code like the Incompat 3D or any of them to really get the scalability and the best performance. So we want the latency to be low. We want high bandwidth communication, but more importantly, we want overlap of computation and communication. So that is the principle number one in any parallel computing. So if you can achieve the overlap, then obviously the communication cost, effective communication cost will go down, and then you will get good performance. And in this particular the assignment, like what you will be working on in the Incompat 3D, as Filippo indicated, will focus a lot on the non-blocking collectives. Okay, and these are the kind of the IE all-to-all examples what Filippo indicated. So what we have been doing here over the last almost 1.5 years, taking a look at the DPU technology, the MAPIS to DPU, what we have come up with, I'll indicate that. Traditionally, for the non-blocking collectives, let's say I do an IE all-to-all, who progress the communication? Because for all-to-all, there has to be a lot of message exchange takes place. And typically, a thread or an additional core does that computation. But then if you run it in a fully subscribed mode, you don't have any cores or threads available to you. Okay, so here we are trying to use the DPU. So think of like the DPU is like a offloading. Okay, and if I show this architecture, some of you might have seen. So this is the DPU architecture. We have a set of host, and then within the node, in addition to the basic InfiniBand RDMA engine, we also have a set of cores. So I call it actually in a very simplified manner, executive secretaries. Think of your host processes are executives and the ARM cores are secretaries. So just like in the regular like a day-to-day world, you try to offload things to the secretaries. Same things we are trying to do it here within the MPI library. So are you people seeing my full screen? I am seeing actually some of the slides below also, just for.
A quick question. Anyone doesn't see the slides?
Full screen, DK.
Huh? You were seeing it in the full screen?
Yeah.
I see the full screen.
Okay, that's good.
Anyone doesn't see the slides besides Donglai?
Yeah, that's what Donglai posted something.
I'm able to see it, Dr. Panda.
Okay, so let's continue. Okay,
let's continue.
Okay, so this is the library which you will be using. This is the 2022 O2 release we made last month. And this is a derivative of the MAPIS library, which many of you might be familiar. This is from the Ohio State. So this uses the 236. In fact, we made a new release MAPIS 2 just 2 weeks back, but we have not taken that yet. But this is based on the previous version. So you have all the features available with MAPIS 236. So you can refer to the MAPIS user guide. It has all the details. But in addition to that, we have a new user guide for the MAPIS DPU, and this is where we have done I all to all, I all gather, IB cast. Okay, at least 3 non-blocking collectives. Mostly you will be using the I all to all, which is there in the Incompat 3D. And we'll show some numbers later on, depending on your sizes, the code, how you restructure, you may be able to go even 100% overlap. Okay, we have seen that with the micro benchmarks, but the question is, can it be achieved at the application level? And that is actually a part of this exercise you will be doing. And effectively in the end, it will help you to get the real benefits at the application level. So at this time, let me hand it over to Nick. You have the user guide. Filippo indicated something at the top level, but Nick can go into more detailed steps. What do you need to do, how to activate this library, and what to do, what not to do. Nick?
Okay, so there's 5 steps for running using a MapIdge2 DPU on the Thor cluster. So the first one is to add this snippet into your bash RC. And this snippet, what we'll do is it will guarantee that you use the DPU HCA. So Thor is a unique cluster in that it has both the ConnectX-6 plugged in and then also the blue field. So adding this snippet is required for you to like reproduce the numbers that X-ScaleSolutions has published. So we can go to the next slide. Okay. So the second step is to allocate resources with Slurm. And an important thing to note is that since the DPU nodes are managed by Slurm as if they were just regular hosts, you have to allocate them in such a way that you're passing the -w option, so that like will give the actual host names that you want to allocate. So it's important to say that you're allocating the 1 through 4 hosts, Thor 1 through 4. Then it's important to pass Thor-BF 1 through 4. And if you have a reservation for the competition, you can also add -- reservation equals and then the name of the reservation at the end. So once you've allocated, or you can also submit with sbatch as well. The arguments are the same for sbatch versus salloc. So then the third step is to create a host file using the nodes that were allocated. And you can use the format hostname : processes per node. So at the bottom, there's an example host file where we have 4 hosts and then 32 processes per node. Alternatively, you can just duplicate each line. So instead of using :32, you can add in Thor 001 32 times and then Thor 002 32 times. And that will have the same effect as the host file below. This is just a convenience option. So then the next step is to create a DPU file. And you can do this by adding the allocated blue field host name, so the -bf hosts. And one constraint with the DPU file is that it does not allow any duplicates. And then also the : operator, like I just described for host files, is not supported with the DPU file. So the reason for this is that MapIdge2 DPU will determine the best number of processes per blue field at runtime. And an example is in the middle of the slide. And then a quick way to generate a DPU file is by using the scontrol show hostnames command. And you can just grep for BF because all of the DPU nodes, the host names, will have a BF inside of the host name. And then if you just pipe that to a DPU file, then you can just use that directly. And then the last step is to call npi run rsh. And at the top is a DPU is enabled example command. So you can see that there's the -host file being passed, and then also the -dpu file. And then you can optionally add mv2 use dpu equals 1. So that is enabled by default. And then one important thing to note is that for -np, you only want to include the number of host processes and not including the DPUs. So you can count the number of host processes by just doing wc-l like in Filippo script if you use the duplicate method instead of not using the : method. And then in order to run with DPU disabled, what you can do is just remove the -dpu file argument and then set mv2 use DPU equals to 0.
Okay, Nick, thanks. Donglai, you can go over these things. Are you able to see the slides? Otherwise, I can cover.
I could not see it.
Okay, that's fine. So let me cover this. Okay. So here are some sample numbers. What we have done. So this is like, let's take a non-blocking all-to-all, and these numbers are all taken with the OSU micro benchmarks. Many of you must be familiar with, which are called OMB. So we are using the standard micro benchmarks to report this number, and you should be able to also get exactly the same numbers. So here what we are trying to do, it is like a 32 nodes. Here you can see on the left hand side 32 nodes 16 ppn. So 512 process runs, and the right-hand side is 1000 process runs. So what we are trying to measure here is the computation plus communication. So Visio micro benchmark allows you to evaluate that. Just like Filippo indicated, for your application, you may need to do like a restructure the code to have I all to all followed by some computation. That's what exactly we are measuring here. And as you can see, the red bars are like basic MHAPIS2. So there we don't have the like the executive secretary kind of a model. So that is not using any DPU. So when you do I all to all followed by computation, the time actually is much more higher. Whereas if you can offload the while the non-blocking collective is taking place by the DPUs, overlap is taking place with respect to computation. So now you can see in this case for different message sizes, we get around like a 20 to 23% benefit, and the right hand side is similarly like a 17 to 22% benefit. So that is the overall execution time, and now you can see the actual overlap numbers again taken from the Visio micro benchmarks. So the way it is shown in the MPI, you have like two kinds of protocols broadly: an eager protocol for short messages and rendezvous protocol for large messages. And most of the time, internal to any MPI library, the eager protocols are implemented with copying. So you get some overlap. But in the eager protocol, you go through a rendezvous. Like I send an RTS, the receiver sends a CTS back. So there is not much overlap. So that's what we see here. If you look at very below here, very tiny small amount of overlap we see for the basic MHAPIS2. Whereas the MHAPIS2 DPU, as you can see, we are able to, for both short and large messages, we are able to really go into, for short messages, we go up to 98%, large messages, we go up to 100%. So that is for I all to all, which you will be mostly focusing on. But here also some additional numbers just for your information. These are for I all gather. That is another kind of a non-blocking collectives. Similar trend with the different PPNs. We are showing the numbers. Here we see like a 41% improvement. As you can see again, 84%, 39%. This is a non-blocking BCAST. Here also you see similar kind of things like a 57%, 48% improvement kind of things. So that is just for at the Visio micro benchmark level. But now let's go to at least one application. What we have done, you will be broadly doing very similar things for you the incompat 3D code. So here we have done a P3D FFT. So this P3D FFT is a package from San Diego Supercomputing Center. So we have worked with the developer. So they were using blocking all to all, just like the incompat 3D. Okay, they were using blocking all to all. We worked with the developer. The developer actually modified it to use non-blocking all to all, and to actually move some of the computation to the slot after doing the non-blocking. And then we ran it with the MHAPIS2 DPU. And now you can see the real benefits. So this is like a 32 node 16 ppn, 512 process run, and these are all on the Thor cluster. So which you will be using exactly on the same hardware. And then here, right hand side is like a 1000 process run. And here you can see like we are able to get like a 16 to 21% benefits. Of course, the benefits changes because of the like the dimension of the P3D FFT. Here we are posting numbers like starting from 1K by 1K by 1K to 2K, 4K cross kind of things. So you might be trying to run similar kind of experiments based on the different data sizes, and then see where you get the sweet spot, where you get the best benefit. Okay, the P3D FFT code unfortunately is not public by the developer, so we are just showing you the numbers. That code is not public, but here as a part of the student cluster competition, you will be actually working on the incompat 3D code, and they will be evaluated. So with this, Hari, do you want to provide the final conclusion, or I can do it?
I mean, either way is fine.
Go ahead. Go ahead. Yeah.
Sure. So hi guys, this is Hari. So far we have given you an overview of, I think Filippo was kind enough to give an overview of how the application modifications were done, and Dr. Panda and Nick and Dangla gave an overview of the MHAPIS2 DPU library. So the main goal here, as Dr. Panda mentioned, was to get good overlap of computation and communication, which is critical to overall application performance. as well as good communication latency. So both are equally important, and we are able to achieve both with MAPIS2 DPU. So MAPIS2 DPU is able to overlap computation and communication for several non-blocking collectives like all-to-all, all-gather, and broadcast. And this, at the end, results in a reduction for the total execution time of dense, let's say, applications like P3D FFT or XCompact 3D, which uses dense collective communications like all-to-all by a significant factor. So we are still continuing to actively develop MAPIS2 DPU to offload more types of non-blocking collectives. And if you have any questions whatsoever, please do not hesitate to contact us, and we'll be glad to work with you. Thank you.
So this is our address, and again, we'll be also be monitoring the Slack and all these things when you are performing the competition. But if you have any questions, this is the address. Directly also you can send us a note, and we'll be very happy to work with you to see if there are any issues. I think that's all. I just want to share. Back to Ophir.
Yes, okay. Thank you, DK. Let's open now for questions. Anyone feel free to just to ask or to put in the chat. Everything is known. So any question from anyone?
So either we were awesome and you guys understood everything, or you guys understood nothing.
I have a general question.
Here, Panos is asking.
Possible.
Sure.
You mentioned many DPU in conjunction with collectives, non-blocking. Is it in your plans to apply this also to point-to-point?
Yes. So those are the initially we took the non-blocking collectives, but we are looking at like even for the point-to-point, we have some things in the pipeline we've been working, and you will see in the next few months those solutions coming out.
Okay, thank you.
Nilesh has a question.
So I think Nilesh raised his hand.
Yes.
Yeah, hi. Is there a profiler that works in conjunction with the DPU, like especially for like monitoring DPU utilization and things?
So currently there is no profiler which will help you monitor how the DPU is working. So that's proprietary information. But regular MPI profilers like MPI-P will definitely work with the host-based code, and it'll try to show you how the overall all-to-all is performing.
Tau also works. You can also use
Tau. Any MPI profiler will help you profile the all-to-all code at the all-to-all level, but visibility into what happens inside the DPU is protected.
So just to extend on the answer. So I imagine that the question was about, okay, this is cool. I can offload communication to the DPU. The library will take care of it for me. How do I measure actually the benefit in the real application? Now, from that point of view, you will have to instrument the application. So most of the MPI profiler allow you to basically say, oh, this MPI is happening. With this MPI call, you have this message size and you consume this amount of time, which is great because it allows you to understand where the communication happened and how big it is and what's the message size and things like that. But moving to this new paradigm, when you post a communication, the execution return immediately to the application. So that execution will only be the time spent by the library to initiate the communication, not the communication itself. So my advice would be to put, and every team can do what they want, but to try to identify a way to mark area in the code, timing area in the code that have not just the communication, but also the computation. And what you will observe is that if you overlap, that time has to reduce because communication will happen with the communication. So it's left after exercise to find what in your opinion will be the best strategy to measure within the application, natively within the application, how much of communication you can squeeze into the GPU and how much computation you can, overlap with it. There is no tool that natively measure that, as far as I know.
Yes. Thanks, Filippo.
It's a coding challenge after all. So, yeah. So
I see my two young kids.
Yeah,
Say
hi.
hi.
hello.
Going to school. Let me add another thing. The bashrc, the .bashrc file, we already fixed that for all the teams, so we don't need to worry about that. You can check in your under your user. David already changed added the lines to allow the different adapters. Note that when you run the application, I want to verify that. So we have two adapters on the Tor nodes. One is the regular Connectix adapter, which has only the networking ASIC with no ARM processors, and the DPU itself, the Bluefield DPU, which has the Connectix itself for the networking, and then an additional 8 ARM processors for computation. And then the ARM side, the ARM processor is running Linux over there. So you can actually go inside if you want, and then get into the adapter, the DPU adapter, and you know, use the Linux over there. For running the application, you don't need to do that. So when you allocate the nodes, you allocate the whole bunch of nodes, and from the script that you run, you will use the mVapage DPU that will do the communication with the DPU itself and will handle all that. So you don't really need to go inside the Linux DPU. Any additional comments, anyone? Remember that you can always find us on Slack. You can always email us any issue that you have. We are using the input that we will send you the specific input for this task, slightly modified, the cylinder slightly modified with the problem size. We will send you the link to use it. It's a short input file. It's based on the cylinder input out of the you know Incompact 3D Git, and then you can use that one. Okay, so
sorry,
yeah.
sorry, Ophir. Just one thing, just to spice up a little bit things. So this is obviously a very the NVIDIA DPU and the mVapage DPU library are pretty new piece of hardware and software. And this idea of offloading entirely on a new piece of hardware computation is relatively new as well. So obviously someone can ask, okay, but is actually this possible to do with a real application? So we are working to build what you're going to do as well for the competition internally, just to prove that things work and to test everything. So by the time you're going to post your solution, we're going to have our own version. We're not going to use that version to rank everyone against it, but it's going to be shown as a reference, probably during the competition itself, during the wrap-up, as how we would have done this type of work. And that will be made open source obviously toward the end. So you're not going to be alone doing this exercise, and we will prove you that there are some benefits that can get out of it. But as a result, we will not really much disclose beyond what we give as a guideline what we are doing internally. So imagine that there is an additional team that is competing, but is not going to take any prize. So we want you to do better than us at the end. So this is very exciting. So try your best.
Thank you, Filippo. Okay, so I think the teams needs to some time to digest all this and to start getting started. Again, if you're stuck, if you need some help, let us know. Communicate with Alf, and we'll do our best. We are here. We are on the Slack. We are on the email. Reach to us. This is for you to learn, to explore, and hope you enjoy it. This is a very leading edge of the technology that available these days, and we hope you use it and explore with it and enjoy it eventually also. So I would like to thank everyone. Okay, Filippo and the DK's team, and Harry and Dongley, and everyone that came. I will put the recordings and the slides later on the website, so you can revisit that, and stay safe. Okay.
Thank you.
Bye-bye.
Okay.
Bye.
Okay.
Bye.
Bye.
Bye
Bye
bye.
everyone.